Hello everyone, this is Chen Zhong, and this is my final presentation for the course Big Data Analysis. Here I will present you with some of my research on the problem of intrusion detection based on the KDD Cup Dataset. Here's the abstract of our problem. First, what is intrusion detection? An intrusion detection system is a device or software application that monitors network or system activities for malicious activities or policy violations. An intrusion detection and prevention system are primarily focused on identifying possible incidents, logging information, and reporting attempts. Here, I will apply some machine learning algorithm to improve the accuracy of intrusion detection to support the system. First, let's see what the data looks like. In the KDD Cup dataset, there are millions of records here, and each of the records is labeled as normal or a particular kind of intrusion. For each intrusion label, there are four main types of intrusion: DOS, probe, R2L, and U2R. And there are 24 subtypes in training set and additional 14 subtypes in test set only. And there are 41 features for each record. First, I tried some simple algorithms on the original dataset. Surprisingly, I got exceptionally high accuracy on the original dataset. But after I did some more research on the dataset, I found out why I got such a high accuracy, which is actually not a good thing. After I did some analysis on the dataset, I found that there are lots of redundancies in the dataset. The redundancies will lead to the bias towards the more frequent records. And those more frequent records will have more accurate detections. And that is why we got such a high accuracy here. And the redundancies will also lead to the result that the dataset is too large for us to analyze. And it also brings us another difficulty. With the redundancies, almost every machine learning algorithm gives us a similar result because the bias toward the frequent appeared records will dominate the results, and we can't compare the performance of different algorithms. Here's the statistics of the dataset after we did the data cleaning. As you can see, the number of the records is significantly reduced. After we did the data cleaning, now we need to move to the feature engineering. Why do we need feature engineering? Feature engineering can help us reduce the data amount because there are lots of features in our dataset, 41 features. And I'm sure there are some features there is useless or irrelevant to the intrusion detection problem. So by selecting only useful features from the 41 features, we can avoid meaningless calculations on the useless features. Feature engineering can also help improve the accuracy. By removing misleading or unrelated features, we can exclude the bad influence from those features on our classification results to improve the accuracy. And it can also help avoid overfitting. There are some features that are correlated with each other, which is actually a repeated features. So by removing the correlated features, we can reduce the possibility of overfitting because we avoid emphasizing some of the features. To do the feature engineering, first I need to find the useless features. To find the useless features, I calculate the variance of values for each feature. As you can see, there are the variance for the 41 features here. Some variance of the features is pretty high and some is relatively low. Here's an extreme example. The feature called non-outbound commands has variance of 0. That means every record in the dataset had a same value for this feature, which means this feature is actually useless for our machine learning algorithms to do the classification. So we can remove this feature from our dataset. There are also some other features that have very low variance. We can remove them. Our next step is to find correlated features. To find correlated features, we can calculate the correlation efficiency between features. I got a very huge correlation efficiency matrix from the dataset, and after reading the matrix carefully, I found some pairs of features which have a very high correlation efficiency. Here are some examples. As you can see, for example, the non-compromised feature and the non-root has a correlation efficiency very close to 1. That means these two features are very highly correlated, and the change of one of the feature can represent the change of the other one, which means we don't need both of them. We can just select one of them to represent the feature. In this way, we reduce some more features in the dataset. Besides this, we also need to do the normalization among all the features so that every feature in the dataset has a similar influence on the results. And we can also do rule-based feature selection. But this selection will require us to have domain knowledge about the intrusion detection. Because we don't have such domain knowledge, we don't do the rule-based feature selection here. Done with our feature engineering, here's my classification strategies. I first did a binary classification to classify all the records to normal and anomaly. Then I will classify the anomaly group into smaller categories, where there are 5 types of intrusion. To do the classification, I tried 4 different classification algorithms: a decision tree, random forest, naive Bayes, and a KNN. First, let's look at the decision tree algorithm. After some trials, I found that when the leaf size is set to 50, I can get a pretty good result. The precision for the binary classification is around 75%, and the precision on the 5 types classification is around 73%. As you can see from the table, in the test data, a lot of anomaly records is classified as normal. This means our classifier tend to misclassify the anomaly to the normal, which means a high false positive rate. And the reason why I use decision tree is that by using decision tree, I can find the importance of each of the features. As you can see, by calculating the information entropy, I find out what features are the most useful. As you can see the table down here, the most important feature here is source bias. And here's the top 10 important features here. The number below the feature names is its importance. With this information, we can select the useful features. The next algorithm I tried is random forest. Similarly, after some trials, I found that when the number of trees in the forest is set to 500, I can get a good result. And the precision on the binary classification is around 76%, and the precision on the 5 types classification is around 72%. And it has a similar problem with the decision tree, which is a relatively high false positive. And next, I tried naive Bayes. Naive Bayes performs better than the previous two on the binary classification with a 77% precision, but on the 5 types classification, it doesn't really work well with a precision only 51%. After I tried those 3 algorithms, I want to try the KNN algorithm, but when I run KNN algorithm on one machine, I found that the process is really slow. So here I tried to apply the KNN algorithm on a distributed machine learning platform under MapReduce framework. There are 2 choices. The first one is R-Hadoop. R-Hadoop is a collection of 5R packages that allow users to manage and analyze data with Hadoop. The language is R. And the other choice is Mahout, which is in Java. Mahout is free implementations of distributed machine learning algorithms, focused on primarily in the areas of collaborative filtering, clustering, and classification. Here, for the convenience of this project, I used R-Hadoop to implement the KNN. Here's the sample code of my KNN on MapReduce. Why I use KNN on Hadoop is that KNN is a lazy learner with very slow classification speed. And the process of KNN is very easy to parallel and to implement on distributed environment. Here's the result I got from the KNN algorithm. After some trial, I found that when K is set to around 30, the result is relatively good, with a precision of 75% on the binary classification and around 70% on the 5 types classification. Okay, all the experiments we done just now all focused on the known labels in the training set. However, as I just mentioned, there are 24 labels in the training set and there are 14 labels in the test set that doesn't exist in the training set. So how do we classify those unknown labels? Here I tried the k-means algorithm. K-means algorithm is used for clustering on labeled data. There are 2 main steps in the k-means algorithm. The first step is the assignment step. In this step, we assign each observation to the cluster, whose mean yields the least within cluster sum of squares. And in the update step, we calculate the new means to be the centroids of the observations in the new clusters. After several iterations, the centroids of each cluster will converge, so that we can get the new clusters. And each of the new cluster will be the unknown labels in the test set. Since we know that there are 14 types of unknown labels in the test set, we can set the key in the key means algorithm as 14 to make every cluster represent an unknown label. Okay, that's all for all my research done with this intrusion detection problem. Here's the summary of my experiments. First of all, I did data cleaning to remove the redundancies in the dataset. Then I did feature engineering to remove useless or irrelevant attributes in the dataset to improve the accuracy and avoid overfitting. Then, with the refined dataset, I did a lot of experiments using different machine learning algorithms, including KNN, decision tree, random forest, and naive Bayes. And for each algorithm, I did error analysis and to find the best parameters that leads to the best result. Then, because of the low efficiency of KNN algorithm, I apply this algorithm onto the MapReduce framework to deal with big data. At last, for the new types in the test set, I used unsupervised machine learning algorithm called k-means to find the unknown labels in the test set. For the future work, I can try more machine learning algorithms using MapReduce framework. In this project, I only put KNN algorithm into the MapReduce framework, but there are also many other algorithms such as neural network and SVM that requires a lot of calculations. But they are more difficult to parallelize on the distributed system, but it is definitely worth doing so. Besides that, I will also dive deeper into the features with some domain knowledge. In this project, because I don't have many domain knowledge about the intrusion detection, I can't select the features using rule-based strategy. But I believe if I can use domain knowledge to do the feature selection, the performance will be significantly improved. And that's all for my presentation today. And if you have any questions, please feel free to contact me. Thank you.